I hope you got this sheet. Did you took them, Taylor? Okay, so if anybody did not bring that back, I have a few extra. If you weren't here last time, Taylor has a few extra because we're going to do that today after the lecture. Don't know what I'm looking at there. Let me switch here. Okay. So, so on the homework list now, I did just a little bit adjust some due dates, but there's still a quiz that's due. This is on the homework that you finished last week. So there's a quiz for that, just that homework. So it's going to be very similar to the homework problems. But so that is due at midnight, okay? Right? And then the next homework is not due right now until Wednesday, okay? So you've only got one other homework due this week, the one that's due on Wednesday. And then these upcoming ones are due on Monday. And then we're finished with Chapter 2. And so that was really the chapter all about linear functions. So we'll finish those notes today, I think. Pretty sure. And then we'll start talking about something that's not linear anymore in Chapter 3. Okay, so that's kind of the list of where we are. On this homework, there were a few problems I was looking and looking at problems that seem to be causing difficulty. Some of those I will look at next time, but I did want to point out. Let me see if I can remember a couple of those. If I scroll through here, the ones that were, oh yeah, okay. So I think a problem like this one was listed one that people were having a difficulty with. This is just a matter of using this data to set up a formula for a linear function. So if you read the data carefully, you'll see that you have really 2 points given on that linear function. So you can use your point slope formula for writing down the equation for the line to write down the formula for this line, okay? But I think maybe what was causing difficulty here is the instructions. So about entering your answer. So be careful to look at those instructions closely, okay? It says you want to round your answers there to 2 decimal places. And so if you have any numbers in your answer, be sure you put them in decimal and 2 decimal places, and that includes whole numbers. So if you had a whole number coefficient in this formula for this straight line, like 2, you would still have to enter it as 2.00, okay? So whenever in WebAssign, when you have those instructions for entering the answers, they're sort of in that light typeface there. Make sure that you read them right, because otherwise you could have the right answer and it won't count it right. So be careful about that. That's often a source of issues. And then other things that were causing some problems were the word problems. So I sort of anticipated that. One of those word problems, a couple of those word problems were very similar to the example in class, okay? One of the word problems was about a piece of bread, right? Do you remember that one? It had calories. It was something about calories with light bread or something. We'll look at that one next time because that was a little bit different from the example that we went over in class. So for some reason, this problem also, so you might have had a different version of this, was also causing some issues, all right? And I think it might be, again, on how the answer was supposed to be entered. So this is just an equation to solve, so it's fairly easy to solve. You may need a calculator to help you with solving the equation, but it should be pretty straightforward. Let's see if we can write down that, see if I can see that equation to write down. So 0.95t, and then plus 0.05, and then 100 minus t, and that's equal to just 0.011 times 100, okay? So this is just a linear equation to solve. This is called a linear equation, again, because the unknowns here, right, are just raised to the first power. We're soon approaching cases where the unknown are raised to higher powers, but here we're still dealing with the most straightforward case. The only thing challenging maybe about that one, again, and I think that was causing the issue, especially in entering the answer, is you just have these decimal coefficients, right? But the steps that you're going to follow to solve the equation are just the same. So I'm going to simplify both sides of the equation, okay? So I want to carry out the arithmetic that I can carry out by hand, right? Okay, using a calculator if necessary. First, right? So we have 0.95t, and then let's multiply through that 0.05 times 100 minus t. Well, 0.05 times 100 is going to be 5, okay? And then we will have minus 0.05 times t, right? Okay? And then on the right-hand side, just multiply the 0.11 times 100, so that works out to be 11. Okay, and then gather like terms, right? So you have a couple of like terms here on the left-hand side, the 0.95t minus the 0.05t, so you have 5 there, and then plus, I guess, 0.9 t, right? Okay, when you take the difference in those two terms, right? Is equal to 11, so that's looking a lot better, and now I can subtract 5 from both sides, or you can think of that as shifting the positive 5 back to the right? That's so we can separate these terms, right? My unknown terms on one side of the equation, and then my constant terms on the other side of the equation. So I have 0.9t is equal to 11 minus 5, which is 6, okay? And then, to finish solving for t there, right, just divide both sides by 0.9, okay? So I come out with something like t is equal to 6 there divided by 0.9, but they want that written as a fraction. They don't want that written as a decimal, okay? So so we want to get rid of the somehow get rid of that 0.9, right? Okay. And you can do that by multiplying, whatever it takes to eliminate that 0.9, right? And that's easy if you just multiply the 0.9 times 10, right? Okay, because this is 9/10, just written in decimal form. So you can multiply that by 10, and that will make that into a 9. Now, however, you don't want to change the value of the fraction, right? So if you're going to multiply the denominator by 10, also multiply the numerator by 10 as well, okay? And you get here 60 over 9, all right? A fraction without any decimals in it. Now, you can actually reduce that, though, because 3 divides into both 60 and 9. So when you divide 3 out of both the top and the bottom there, you end up with 20/3. So we can enter our answer there as 20/3. We don't have to enter it as a decimal. And that's what they were trying to get you to do, okay? So if you got to the 6 divided by 0.9, that's good, okay? That is the solution to the equation. They just wanted it written there in a slightly different format, okay? So apparently 20/3 is the same as 6 divided by 0.9, all right? So if that's what was tripping you up, it was just how they wanted the answers entered there. Okay. All right. So again, there were a couple of other word problems that people also either missed or had to work on it multiple times. So we'll look at a couple of those, but two of them were very similar to the example that we did in class last time. All right, that word problem about that rectangular word problem, right? So that's a good example to follow, also to help with those two. Are those word problems. So you might have some like that. I didn't look this morning at the quiz, but you know, you might have some similar problems, right, to these homework problems on that quiz that's due, this one, that's due this evening. Okay. So now, remember these, as always, right, these problems that if you're having difficulties with, right, you can go to the Math Center because they've seen these problems lots of times, so they can explain them to you very easily, right, okay, or very well in the Math Center. If you are having access issues at home, so if you are not don't have good internet access at home to do your homework off of campus, what you can do is print your homework while you're on campus. So you can print a copy of your homework assignment. There is a print option there, or should be a print option in the homework, so you can print out a hard copy of it, and then you know, you can work on that anywhere, and then just enter the answers that you get when you're on campus and you do have internet access, all right? So that will give you an option for, you know, working offline, right? Okay, print the homework, work on it somewhere else, and then you know, bring it back, and then all you have to do is just type in the answers when you're on campus. That won't take too long if you get the questions right. Of course, if you get some of the questions wrong, then you'll have to worry about fixing those, right? Okay, but that will save you a little bit of time on campus if you don't have time just to sit here and do the homework, okay, while you're here. Okay, are there questions? So I blew through a bunch of things there without asking y'all, but any questions there on anything? All right, so we want to finish our notes now for chapter 2. So I'm going to look at that, and we were last time just had one example of instead of solving an equation, solving an inequality. But we're going to look at a couple of more examples here right now of solving inequality. So this work is going to work very similar to solving equations, at least initially, okay, if you have what's known as a linear inequality, which is similar to a linear equation in that you have the unknown just raised to the first power. So let's look at this example B. That counts as a linear inequality because the unknown z there is just raised to the first power, right, on both sides of that inequality. And with these, if that z were squared, on the other hand, or if that z were in the denominator of one of the terms in this inequality, then that would be a much tougher inequality to solve. Inequalities can get tricky to solve quickly, much more quickly than equations even. But if you just have your unknown raised to the first power, then you treat it very much like an equation. With that one little caveat, right, that we saw last time, that if you multiply or divide both sides of an inequality by a negative number, not just any number, but it has to be a negative number, then you've got to remember to flip the direction of the inequality. Otherwise, you'll get the solution exactly backwards, all right? So, so just keep that one little exception in mind, but otherwise, treat this like just like it's an equation. So just like in this example, what I'm going to do is simplify both sides of the inequality first, right? So I'm going to multiply that minus 3 through, going to multiply this minus sign through these parentheses, and then we'll gather like terms together, right, on both sides. So minus 3 times 4z, that's minus 12z, and then minus 3 times minus 4 is plus 12. Be sure you distribute that minus sign properly, right? So don't get sloppy when you're multiplying the minus 3 into the parentheses. Multiply it carefully by both terms. And then greater than or equal to, and now minus times z minus 1. So that would give us minus z and then plus 1, right? Okay. Let's see, do we have any like terms? Not really on the left-hand side we don't, but on the right-hand side we can add these constants together. So you have 4 plus 1, which is 5. So you end up there with 5 minus z, right? And now we want to separate terms, right? So I want my unknown terms, my z terms on one side of the inequality, and I want my constant terms, the 12 and the 5, I want them on the other side of the inequality. So you can rearrange things however you wish, all right? Let's move the minus z back over to the left-hand side, so I can put it with this minus 12z. And then let's put the 12 back over on the right-hand side. So I get minus 12z and then plus z, when I shift that z over. And then let's see, on the right-hand side, I'll get 5 and then minus 12. So I end up with minus 11z here is equal to minus 7. Okay, whoops, not equal. That's another common mistake, and I already told you I like to do this too, this same mistake, right? I changed the inequality in the middle of the problem to an equal, right? And that's very easy to do because you're used to writing down equal marks, but you're not used to writing down inequalities that often. So we end up with what? Minus 11z is greater than or equal to minus 7. And now I have to get rid of that coefficient of minus 11. And here's where I have to be careful, right? Because to get rid of that coefficient, I'm going to have to divide both sides by minus 11. That's a negative number, so I have to flip the direction of the inequality. But if I were dividing by positive 11, I would not have to do that, okay? So it's only dividing by negative numbers that makes a difference. So I get what? Z is less than or equal to, and then minus 7 over minus 11 is 7/11, all right? So there's the solution to my inequality. Any number will be a solution to that inequality as long as it's less than or equal to 7/11. So apparently 7/11 is the biggest number that's going to be a solution to this inequality. Okay. All right. So it's really okay to write your solution down as this final inequality here. That's pretty clear what the solution is. But you can also write this down in interval notation, numbers less than or equal to 7/11. So that would be any number starting at minus infinity, right, and then going up to 7/11. Numbers less than or equal to 7/11 are in this set, right, from 7/11 down to minus infinity. And since this is less than or equal to, you want to close that interval with a square bracket because 7/11 is part of the solutions to that inequality. So these two things mean the same thing. All right, they're just both ways of writing down the solutions to that inequality. So this next example. This also is just a linear inequality. Because again, here x is raised to the first power, here x is raised to the first power. So again, we can treat this much like a linear equation. Okay, so it's not an equation, right? But we can go through the steps of solving that inequality just like it was an equation. So this one has some fractions in it. So what's our recommended strategy for dealing with the fractions? I'd like to get rid of those quickly. That's my strategy, okay, is to, if possible, eliminate the fractions, all right, because fractions are so messy to work with. So, but what technique can I use to eliminate that 4/9 and that 3/4?
You can divide it by itself, but flip it around, so...
So you're thinking of doing what, Montel?
To get the fraction.
Well, we got two fractions, so which one were you thinking about?
I was thinking about 3/4.
The 3/4, okay. So how can we get rid of the 3/4, Montel?
Divided by itself, but you would have to flip it around, so it would be 4.
So multiply this by 4/3? Yeah, but remember, when I multiply that by 4/3, I'm going to have to multiply everything by 4/3, okay? Because I can't just multiply this one single term. I have to multiply everything in the equation by 4/3. That will eliminate this fraction. You're right. That would make that 4/3 times 3/4, which is 1. But you would also have to multiply the 7 times the 4/3, and I think I'm going to end up with another fraction there, okay? So I really won't be eliminating the fraction. I'd also have to multiply the 4/3 by this side as well, and I think the 4/3 times the 4/9 is just going to end up with a messier fraction, okay? But you're right. Multiplying, at least partially correct there, multiplying by something is the way we want to go. But the question is, by what? All right. So can you think of something we can multiply here by so that I can get rid of the fractions and not end up with any more fractions left? What was the great thing of multiplying this by 4/3? You ended up with just 1. But what was really helpful was I really didn't need to multiply it by 4/3, okay? What really helped is multiplying by the 4, not the thirds part. Because if I multiply by 4, what's going to happen to this fraction? Montel, what's going to happen to this fraction if I multiply by 4? This one. You'd be left with the 3, right, okay, which is better than a fraction. See, the 3 is not a fraction, right? So there's something I could do, I think, and multiply by 4. But I have the same issue here, Montel. What could I multiply there to get rid of that 9? Multiply by 9. So is there some way that I can kill 2 birds with 1 stone? All right, can I multiply by something that will get rid of both the 9 and the 4 simultaneously, because I want both of those denominators to go away, right? Okay, so is there some number I can multiply by to get rid of both of those at the same time? What's the trick there? Yeah, which is what? Not 18, but close. Not 28. 24. 36, there you go, right, okay, yeah, I'm going to multiply everything by 36, okay, which, by the way, happens to be 4 times 9, all right, is 36. Multiplying by 36, so I'm going to multiply this side by 36, all right, and then I've got to multiply both of these things by 36, the 3/4, but also the 7, okay, I also have to multiply the 7 by the 36. That 36 is the same as 4 times 9, by the way, okay? So that was really equivalent, Montel, to multiplying by 4 and then also multiplying by 9. Multiplying by 4 to get rid of this 4 and multiplying by 9 to get rid of that 9, you see, okay? That's, in effect, what I did when I multiplied by 36. I multiplied by both 4 and 9 at the same time, okay? All right? And so that's it. There's the game that I'm going to pull. So 9 goes into 36 4 times, so you end up with just 16 times x minus 2, right? Because the 9 divides into 36 4. 4 times 4 is 16. And then on the right-hand side, let's see, 4 goes into 36 9 times, right? 9 times 3 is 27. So I have 27x plus, and then I got to figure out what 7 times 36 is. So a calculator there would help us with that. But I'm thinking it's 252. Did I do that right? Is that what 7 times 36 is? Okay. Okay, right. All right. So so still a little messy, okay, but not messy in the sense that we have any fractions in it, right? So remember that game of eliminating fractions by multiplying everything. You've got to multiply everything by the least common denominator, okay? All right. Now let's just proceed. So I have 16x minus 32 greater than or equal to 27x plus the 252, right? Okay. And now we just want to rearrange our terms. Here, I'm going to be a little bit more strategic than before. Let's put the 16x over on the right-hand side. So I'll have 27x minus 16x, and that will give me 11x. So I won't have a negative coefficient on the x. And then let's bring the 252 back over there to the left-hand side. So I get minus 32 minus 252 greater than or equal to, and then 27x minus 16x. So I can do the right-hand side. That's 11x. Y'all got to help me with the left-hand side. What's minus 32 minus 252? So what's that subtraction turn out to be? Negative 284? All right, and now we're in great shape. We're just here ready to find that solution, right? So divide both sides by 11. Is 284 a multiple of 11? Does 11 go into minus 284? Or do I have another nasty solution here? Someone with a... Can y'all try that with the calculator there for me? It's going to be negative.
It's going to be like 25.8181.
Oh, okay, all right. So we'll just leave it as we'll just leave it in that form. All right, okay. So, I just made that problem up, so I didn't have any idea what the I didn't check it beforehand, so I didn't have any idea what the solution was going to be there. Okay, all right. So kind of an ugly solution there, right? But there it is, minus 289 over 11. I don't think that reduces at all because 11 is a prime number. So so that's it. All right, unless we want to write it as a decimal, but I think we can leave it in this exact form. Is better. Notice I did not flip the inequality here, right? Because I divided by positive 11. Even though I divided 11 into a negative number, I don't have to reverse the direction of the inequality. So, so don't overdo it when you're, dividing both sides of an inequality by a number. You don't always have to reverse the direction of the inequality. So there's my solution, right? Anything less than or equal to minus 289 over 11. So again, that's going to be numbers to the left of minus 289 over 11. In interval notation, that would be from minus infinity up to minus 289 over 11, including that boundary value, right? Okay, because this is less than or equal to, and minus 289 over 11 is equal to itself. All right. So, really, very much like, right, solving equations. Let's look at an application here. This one's kind of interesting. All right, so sometimes when you're hearing the weather report, the meteorologist will mention the dew point, okay, what the current dew point is. And so that's a little bit different from air temperature, okay. The dew point is the temperature at which water will condense on an object. So you notice this especially in the summer. For those of you who wear glasses, right, when you're in an air-conditioned building, okay, and you walk outside, okay, after you've been in the AC for a little while, you walk outside in the summer and, you get a fog on your glasses, right? That's because your glasses have been cool, right, because you're inside the building, and so they're below the dew point temperature, okay? So if an object is below the dew point temperature, that means that the water from the atmosphere, the humidity in the atmosphere is going to condense on that object, okay? So today, as it turns out, the dew point is currently, when I came over here, 64 degrees, okay? So below that temperature, an object below that temperature water's going to condense on that object, or can possibly condense on that object. Okay. Of course, the air temperature is just the air temperature, right? Okay. The temperature that you feel. All right. So now, sometimes though, okay, it will happen that the air temperature is less than the dew point temperature. Normally that's not the case. So today that's not the case. The air temperature outside when I came over was 70, all right, but the dew point temperature was 64, okay? But sometimes the actual air temperature will be less than the dew point temperature, all right? So that happens from time to time, especially in winter that can happen. So air temperature is below the dew point temperature. So when the air temperature is below the dew point temperature, guess what happens? So if you go outside and the current air temperature is already below the dew point temperature, what's going to happen? Or what could possibly happen? It doesn't always happen. Other conditions can intercede, but what can possibly happen in that case? Not freeze, okay, right, okay. That's a different sort of temperature, right? What, Kevin? Yeah, that's right. If the current air temperature is below the dew point temperature, that means water's going to start condensing in the air, okay? And when that happens at ground level, you see that as fog, okay? But now, if that happens in the atmosphere, all right, if that happens in the atmosphere, you're not going to see that as fog, of course. You're going to look up instead and see what? Clouds, sure, right, okay. You're going to look up and see clouds, okay. So clouds form in the atmosphere, right, when the temperature in the atmosphere is less than the dew point temperature, okay. But that happens because as you increase in altitude, okay, as you go up in altitude, both the dew point temperature and the air temperature will drop, okay. The higher you go up, of course, it's going to be colder, right, all right. So as you go up in the atmosphere, both the dew point temperature and the air temperature will drop. Here is the formula now that actually governs how the air temperature changes, okay, in the atmosphere, all right? So notice what sort of, by the way, this is a constant. This is the air temperature at the ground. So today, of course, that varies from day to day, right? But today, that number happens to be 70, okay? All right. So in this formula for today, we could fill in 70. We would get 70 minus 29x, okay? So there's the formula you can use to predict, right, or determine what the air temperature is going to be at a particular altitude. So in this formula, x represents altitude. It's measured in this case, in miles. Of course, what sort of formula is that? That's linear, right, okay? That's linear. The slope here, of course, is minus 29. This is the ground temperature, 70. That's the y-intercept of this linear function, because that is the temperature when x is 0, right, okay? When x is 0, that means you're on the ground. And we said the current air temperature on the ground here is 70, all right? So just plug in the altitude above us, okay, and you can use that formula to determine what the temperature is going to be at a particular altitude. Notice the slope is negative, so that means, of course, as the altitude increases, the air temperature is decreasing, right? Okay? Well, you all know that, right? Okay? The higher you are, the cooler, of course, it is. The same thing happens with dew point. So the further you go up in the atmosphere, the dew point also goes down. Here's the formula that governs dew point. All right. There's the formula that governs dew point. And so, again, this is a constant. Currently, it's 64. All right. Well, notice, so we could fill in 64 here, right, for the d sub 0 for today. So notice that also is a linear function, right? That also is a linear function, okay? and it also has negative slope. So that means that as x increases, as the altitude increases, the dew point also drops, okay? The dew point also is dropping. But which is dropping faster here? As our altitude increases, which is going down faster? Well, what's the rate of change there? What's the slope for the air temperature? How fast is the air temperature dropping? 29. So that tells you what? As x increases by what? 1, right? What's happening to the temperature? It goes down by how much? 29, right, okay, it goes down by 29. So you go up a mile in the atmosphere, right, above where we are, the temperature will have dropped by, the air temperature will have dropped by 29 degrees, okay, right? The dew point temperature is also dropping, right, but its rate of change is only what? 5.8, that's right, okay? So the dew point is not dropping nearly as rapidly, right, as the air temperature is, okay? The dew point is falling, but not as rapidly as the air temperature is. So that means eventually, right, in the atmosphere, what's going to happen? The air temperature is going to drop below the dew point temperature, right? Okay, if you get high enough in the atmosphere, because this value is dropping so much more quickly than this value. So if you go up high enough in the atmosphere, the dew point will get below the air temperature, and then what happens at that point in the atmosphere, or what could happen at that point in the atmosphere? What? Fog, yeah, but it's in the atmosphere, so we observe that as what? Not fog, but clouds, right? Okay, yeah, right. So when that air temperature drops below that dew point temperature, that's where clouds can form, all right? Okay, now, they won't always form at that location because other things also affect whether clouds form. The wind, okay, the currents at that altitude, and so on and so forth, okay? But that would be the sort of the minimum altitude where clouds could form. So let's figure that out today. What is, right now, right, at what altitude can clouds form? So if we're looking up and seeing clouds, and I think there are still some clouds outside, okay, not like this morning, right, but there are still some clouds outside. Let's see what we think that altitude might be, right, okay? So clouds are going to form, right, okay, where, what did I say, the air temperature falls below what? The dew point temperature, right. So what we're trying to figure out is where is the air temperature, I'm calling that T in this example, where does that get less than or equal to the dew point temperature? It's going to be at that altitude where clouds, we can see the clouds, or where the clouds will form, all right? Let's see. So I'm trying to solve this inequality, correct? That's the inequality I want to solve to answer this question. What's my formula for T? 70 minus 29x, right? Okay, so that's 70 minus 29x, and that's less than or equal to, what's my formula for dew point there? Yeah, 64 minus 5.8 times x, and now we just have to solve that inequality, right? Well, now we're pretty good at that, right? So let's see if we can do that. Let me shift terms around. So I'm going to move that minus 5.8x back over to the left, and then let's move the 70 back to the right. So I have minus 29x minus, plus 5.8x, because that sign is going to change, right, is less than or equal to, and then 64 minus 70, right? When I move the 70 back over to the right, that becomes negative. Now let's see if we can do this arithmetic here. Minus 29 plus 5.8, I think that's minus 23.2. But y'all better check me on that. Is that right? Oh, no. Oh, yeah, that's right. Okay. So minus 23.2 times x less than or equal to minus 6. Right? And now easy to continue solving here, just divide both sides by minus 23.2, right? But when you do that, remember you've got to reverse the direction of the inequality because here we're dividing by negative. So I end up with x is greater than or equal to minus 6 over minus 23.2. And let's use a calculator to give us a decimal approximation for that, okay? So minus 6 over, that's supposed to be minus 23.2. So with a calculator, what do we get there? Say to one decimal place. Emiliano, what's that to one decimal place? Minus 6 over minus 23.2. Try to give me a little bit more accurate answer than that, okay? How are you doing that? Oh, okay, you're looking there. All right. So what is that? Emiliano, do you have anything to calculate with? Yeah. Can you pull it out and actually do the calculation for me? We're in a college class, Emiliano, so yeah is not the way we answer our professors, all right? So try doing that calculation for me. .2586. All right, so let's write down that. Let's go ahead and write a couple of decimal places since that's already less than 1. So to a couple of decimal places, about .26. Okay? All right. So so at that altitude, right, greater than or equal to, this is miles. So greater than or equal to 0.26 miles is where apparently those clouds are forming that we can see outside. Or at least the ones I saw when I walked over. How many feet is that? Because might be interesting to know that in feet. So that's in miles, right? How do we convert that to feet? So what's 0.26 miles in feet? How many feet are in a mile? Yeah, okay, perfect. Okay, so just take the 0.26 and multiply by 5280 there, right? Okay, so you're going to get about a fourth of that, right? What is that? What now? 1,372.8. So about, okay, so 1,372.8. All right, good. All right, so in feet, right? Okay. So I'll put the apostrophe there for feet. So the clouds that we're looking at there are a little bit over 1,000 feet up. Okay, I think. All right. Okay. At least that's the minimum altitude at which the clouds could form today. Now, sometimes you usually don't see this with equations, but sometimes with inequalities, you'll have a string of inequalities put together, okay? These are called compound inequalities. So what this inequality is saying is that this quantity, 5x plus 1, okay, that quantity, 5x plus 1, is greater than or equal to minus 4, but at the same time less than 21, okay? So that expression, that quantity, is somewhere between these two values, okay? And but to solve that inequality means I'd like to have just x here in the middle rather than 5x plus 1. So if the quantity 5x plus 1 is between these two values, then can I capture x also between two numbers? Okay. Since this is a linear, again, still a linear compound inequality, because x there is raised to the first power again, this is pretty straightforward to solve, okay? You're going to try to isolate the x. You're going to try to isolate the x in the middle of that compound inequality. And so you do that by trying to get rid of the 1 here from the middle, and then also trying to get rid of the 5, all right? So you'll just have x there by itself. All right, let's start with the 1, okay? So if this were an equation, right, you could eliminate the 1 from this part of the inequality by subtracting 1, right? But you'd have to remember to do that to the other side of the equation. Well, same principle is going to hold here. If you subtract 1 from the middle part of the inequality, you're also going to have to subtract it from the left part and also from the right part of the inequality. So just like with an equation, what you do with one part of this compound inequality, whatever operation you perform on one part of this compound inequality, you have to perform that operation on all 3 parts. So if I subtract 1 here, got to subtract 1 on the left, and I also have to subtract 1 on the right. So it's not quite as easy as, you can't think of this as, say, taking the plus 1 and moving it back over to the, you can't think of this as taking the plus 1 and moving it back over to the, say, the right-hand side. That won't quite work. Or you can't think of taking the plus 1 and moving it back over to the left-hand side. That won't work with a compound inequality. All right, but the adding minus 1 to all 3 parts, that works fine. So I get what? Minus 5 less than or equal to 5x less than 22, right? Oh, 20. And see, now I'm in a little bit better shape, right? Because now I have 5x instead of the 5x plus 1 in the middle. So same principle applies. Now I want to isolate the x in the middle, so I've got to get rid of the 5. Remember, that 5 isn't added to the x. That 5 is multiplied by the x. So to get rid of the 5, I have to divide by 5. So I'm going to divide the middle part by 5. But then if I divide the middle part by 5, then I have to divide all 3 parts by 5 simultaneously. So I get minus 1 less than or equal to x less than 4. And that is the solution, okay? If 5x plus 1 is between minus 4 and 21, then x itself has to fall between minus 1 and positive 4. So there's the solution to that compound inequality. Any number that's bigger than or equal to minus 1, but at the same time, it's got to be at the same time less than positive 4. If you write that down as an interval, that would be numbers starting at minus 1 and going up to positive 4, right? That's pretty obvious how those two things relate, including minus 1, because x can be equal to minus 1, but x cannot be equal to 4 because this says that x has to be less than 4. So on the right-hand side of that interval, you need to put a parenthesis, okay? That's it. Let's try something out of this interval and check to see if it really is a solution. It's supposed to be, right, that every number in that set is supposed to satisfy that original compound inequality. Sometimes it's good to check. When you solve an inequality, sometimes it's good to check your answers this way. You can't completely check the answer because you can't try every number in this set, right? But sometimes it's good to test at least one number out of the set to see if it really does work. What's a number in that set? So help me with a number in that set. Danny, what's a number in that set? This set. 2, right, sure, okay, because 2 is a number between -1 and 4, right? So you can really pick any random choice there that you want. And so let's plug that back in and see if that really does satisfy the inequality. If it doesn't, then that means I should recheck my work, right? So let's see, I have -4 less than or equal to, this is 5 times 2 is 10, right? Plus 1 is 11, is less than 21. Is that true? Danny, is that true? So what I wrote down there, is that correct? Well, let's read it there. So is -4 less than or equal to 11? Yeah, that is true, right? And is 11 less than 21? Yeah, right. Okay. So so that's a correct statement. So so I think 2. Well, I don't think. I know 2 really is a solution to this inequality, and that gives me some confidence, right, that maybe I have the right set of answers there for that one. Let's try this one too. I'm going to show you another approach to this one because we're going to start a little bit more now that we're getting into Chapter 3, where our equations and our inequalities get harder to solve by hand. Okay, not impossible always, but they're going to get harder to solve by hand. And since that's the case, we're going to start exploiting graphs to help us solve equations and inequalities. Okay, and this is but this one now we can solve by hand pretty easily, so we'll solve it initially here by hand. But I want to show you now how you could also look at this one graphically and come up with a solution. All right, so but let's start here just by solving it by hand. By the way, when we say solving like equations by hand, sort of the technical term for that is analytically. So I'm going to solve this analytically just by hand with pencil and paper, and then we'll come back and look at a graphical solution to this inequality, which is not really helpful for this inequality, but again, as I mentioned, our inequalities are getting ready to get significantly more difficult. And then sometimes the analytical solutions, the by hand solutions, are not so easy, but the graphical solutions then turn out to be the easy method to think about the problem. All right, so let's start here. What I want to do first, remember, I want to isolate now the t in the middle of this compound inequality. So we have to start kind of simplifying that middle, right? So how could I multiply by 4? Yeah, multiply everything by 4, right? So the left and the right as well, plus the middle. So whatever you do to one part of the compound inequality, you have to do that to all 3 parts. So I'm going to multiply here by 4, and then also here by 4, right? So I get 2 is less than, and then these 4 divide out. See, and that looks now really easy, right? 2 is less than 1 minus t is less than 8. Now I guess I can get rid of that minus 1. So I'm going to subtract 1 from all 3 parts of the inequality. So I get 1 is less than minus t. Remember, that's minus t now, is less than 7. Okay? And almost got it, because I want t in the middle, but I have minus t. So not quite got it, but how can I get rid of that negative sign? Divide by what? Well, 1 won't do it, but close, Furman. Divide by what? What now? Negative 1, right. Not 1, Furman, but negative 1. Okay, all right. Because you want to get rid of the minus sign, right? If you just divide by 1, you don't change anything. But I want to divide by minus 1. And see that, so I have very nicely there in the middle t. But again, here's that situation, right? You're dividing the three parts of the inequality by a negative number, so I have to reverse the directions of the inequality. So I have minus 1 is greater than t is greater than minus 7, all right? That's it. So there is the, that's it, right? There is the solution. Any number, you got to read it kind of in this direction, right? Any number that's less than minus 1, but at the same time bigger than minus 7. Minus 1 is bigger than minus 7, so this is a legitimate inequality to write down. How would we write that set in, how would you write that in interval notation? So what's that going to look like as an interval? Yeah, it's tempting to put this, right? But that's wrong, correct? What's wrong there? So if I write this down, what have I done incorrectly? Yeah, these numbers are out of order, right? Okay, so in interval notation, you've got to get your boundary values in order. So minus 7 is less than minus 1. So it needs to be written like this. That's another common mistake, easy to make, all right? But the left boundary value has to be less than the right boundary value in interval notation. So there's the correct way of writing down the solution set. So any number between there between minus 1 and between minus 7 and minus 1 should satisfy that inequality. Let's check a number between minus 7 and minus 1. Juliana, what's a number between minus 7 and minus 1? Negative 3, right? Okay, right? Just pick one that's easy there, right? Minus 3, and let's just check it and see if we think it works. So I have 1/2 is supposed to be less than 1 minus a minus 3 over 4 less than 2. Is this right? Let's see, 1/2 less than 1 minus a minus 3 is 4. So I get 1 is between 1/2 and 2. Is that true? Think so, right? Okay. Definitely that is correct. All right. So so when we check it with minus 3, that satisfies the inequality. So it gives me at least a little bit of confidence, right, that I've got the right solution set. Okay. Right, let me show you a method here of going about this graphically, finding this solution set, okay? So you do have to think about it now a little bit differently. We're not going to write down all these steps, okay? But I do have to have do a little work here. What I'm going to do is I'm going to think of these three expressions, the one on the left, the one in the middle here, and the one on the right. I'm going to think of those as formulas for functions, okay? Formulas for functions. So let me write down those three formulas. They're easy to write down. Take the part on the left and just think of that as the formula for a function. So I'm going to write down just y equals 1/2. And then on the right, I'm going to write down just y equals 2. By the way, when you graph y equal 1/2 and y equal 2, I'm getting ready to graph those functions. What sort of picture will you get, by the way? So what does y equal 1/2 look like when you graph that? That's a very simple function formula, so it has a very simple graph. What does the graph look like? Remember, when you have just y equal to a constant, it's a horizontal line. That's right. That's just going to be a horizontal line. That's a linear function. The slope is 0, okay? So when you graph that, you just get a horizontal line, and its y-intercept is 1/2. So it's a horizontal line that goes through 1/2 on the y-axis. We'll see that picture in just a moment. This is the same thing. It's a horizontal line, but it goes through 2 on the y-axis, okay? Now, of course, this is going to be a little bit more complicated, so I'm going to graph y equals 1 minus t over 4. But when you graph that, you still get a straight line, because this is a formula for a linear function. This is the same as 1/4 minus 1/4 times t. You can break that fraction into 2 parts. You don't have to make the graph. I'm just trying to point this out. When you break this up into 2 parts, you get 1/4 minus 1/4 times t, and that's a linear function. The slope is minus 1/4, and the y-intercept is 1/4. So when you graph this formula, you also get a straight line. So I'm going to make all of those graphs, but I'm not going to make them by hand. It'd be easy to make by hand, but I'm going to have the computer plot them for me. So there, I graphed there all 3 of those linear functions with the computer. So there's y equals 2, right? Okay, and there is y equals 1/2, horizontal lines, and then there's that other line, right, where the slope was minus 1/4, okay, right there. Now, how does that picture help me solve that inequality? Remember, what was the inequality? We wanted what? The 1 minus t over 4, right? We wanted that to be bigger than 1/2, but less than what? 2. Where in this picture is this line between these 2 lines? Here's the line y equals 2. There's the line y equals 1/2. So where is this line between those 2 horizontal lines? Let's see, where does that, that's this piece right here, correct? There's the piece where 1 minus t over 4 is between 1/2 and 2. Where does that start at on the horizontal axis? Where does this piece where the line is between the 2 horizontal lines, where does that start at? Where does that look like? Right here? -7, right, okay? It starts right there at -7, okay? And where does it end at? -1, right, okay? So what that tells us is sort of what we had discovered analytically, right? Okay? This expression is going to be between 1/2 and 2 when t is what? Bigger than -7, right? But at the same time, what? Less than -1, okay? So we can also read the solution there off of that graph. Well, look, to solve this particular inequality, we didn't really need the graph, right? Because we could do that by hand. So we had already solved it by hand, all right? But the moral of the story is here, look, inequalities can get notoriously difficult to solve really fast. It's easy to write down an inequality that looks simple, but it's really hard to solve by hand, okay? But these graphical methods can give us nice ways of thinking about or estimating the solutions to these inequalities, even when they're really hard to solve by hand, okay? So this gives us an alternative method. This graphing idea is going to give us an alternative method to solving equations as well, okay? But inequalities when they turn out to be really difficult, okay? Or sometimes even intractable to solve by hand, all right? So keep this in mind, because we're going to exploit this, okay, a little bit later. Okay, I got to show y'all one more thing here, all right, or the or our worksheet is not going to work anyway, so I need to continue a little bit here with the notes. Let's take a break, okay, since I have to talk a little bit more. So let's take a break for a few minutes here, and then let me come back and finish these notes, and I don't know if we'll get to the worksheet today or not. If not, we'll start with that next time, but I got to finish these notes or the worksheet won't make sense. So let's take a break, and then we'll come back and look at these. You'll be able, however, to, your next homework, I think we're through the notes for that, okay? So you'll be able to work on that, even if we don't get completely through with this, all right? So let's come back at about 12:45 and let me show you this last part. Yeah?
You handed that out on Wednesday?
Yeah, I handed out Wednesday, so Taylor's got them. Taylor's got them. Okay. I'm sorry to make y'all watch some more notes, but I just got to get through this. But this is the end of chapter 2, so and we can go on to we can get away from linear functions here for a while and talk about something a little bit more advanced as soon as I can get through these notes. What I'm going to show you now is just a slight variation on linear functions. But these types of functions appear often in applications, so it's important to understand them because they're useful in modeling different practical situations. So what's drawn here is this is the graph of a function, right? Okay. But you don't have just a completely smooth curve here, right? Actually, you've got a curve, a graph here that's formed from really 3 separate pieces, right? All 3 of which are straight lines. So you've got this a line with positive slope on the left. That's part of the graph, and then you've got this horizontal piece in the middle, right? And then this part on the right, which has negative slope. But still, taken all together, that's the graph of a single function because you don't have any input there that matches multiple outputs, right? So in this description of this application, this function is used to model the amount of water in a reservoir, okay? And so you can see what's happening over time because the input x here is elapsed time. So what's happening over time is the reservoir is increasing, right? It's filling up, and then it plateaus at a certain amount, and then apparently the reservoir drains, right? Okay, back down to at 50 hours. Apparently the reservoir is empty there, right? So this type of function that's kind of pieced together from different lines, this is called a piecewise function. Piecewise because it's made up of several different pieces. In this case, all the pieces are straight lines, so this is referred to as a piecewise linear function. All of the pieces, all the individual pieces are straight lines. So that's why the title of this set of notes is what it is. Actually, I could throw in here piecewise linear functions because we're only going to look at piecewise functions where all the pieces, the individual pieces are straight lines. All right, let's see what questions were asked about this particular piecewise functions, this particular piecewise linear function. Most of them are really simple, straightforward questions. First one there is very obvious, right? What are we being asked in that? So this is a test 1 question. What are we being asked in that first part A? So what is that question asking us in words? It's in there in mathematical notation, right? But what are we really being asked here? When someone says, is y equals f of x? Yeah, is y a function of x, right? In other words, do we have a function here, right? Okay. Is this graph the graph of a function? We already mentioned, right? Sure. That's the graph of a function, right? Each input matches their just one output. And then next, again, this is a really basic question. We just want to find the x and the y intercepts, right? Okay, and just interpret the meaning of those. So let's see. Let's start with I wrote down the x-intercept first, but let's start with the y-intercept. That's easy. So what's the y-intercept here, apparently? 2, right, okay. So we have a y-intercept there of 2. And what is that, what's that y-intercept telling us, right? So what's sort of the practical meaning of the y-intercept being 2? 2,000 gallons of water, but you have to say a little bit more than that, Kevin. 2,000 gallons of water, well, yeah, okay, in the reservoir, all right, yeah. But again, this is a y-intercept, right? So a y-intercept always matches input what? 0, right? Always matches input of 0, right? So you need to include that in your interpretation. What? Yeah, after no hours elapse, probably wouldn't say that in conversation. What's he trying to say? What's the easier way of saying no hours have elapsed here? Ben? Well, yeah, 0 hours, but you wouldn't say, if you were talking to someone, you wouldn't say after 0 hours have elapsed, right? From the start, right, okay, at the start, right, okay, or initially, right? Initially what, Kevin? Yeah, so, yeah, that's right. So the initial reservoir level was 2,000 gallons, right? Okay, at the beginning, there was 2,000 gallons in the reservoir, right? Okay, and the x-intercept also easy to see, right? There it is, okay? So you can just read it off of the graph. So what's great about graphs, right? You can just read things off of the graph. So what's the x-intercept there? 50, right? Okay, so what's that telling us? You can almost just see it there in the picture. So what now, Skylar? Is that right? There are 50,000 gallons of water? Yeah, there's no water, right? Okay, but when does that happen? Remember, this is x-intercept, right? So these values are x values, which are what? So say that again. Yeah, after 50 hours, right? There's no gallons of water. You probably wouldn't say there's no gallons of water in conversation. What would you more likely say there? After 50 hours, what? What's a more likely way of saying there's no gallons of water? There's no more water, or what about the reservoir? It's empty, right? Okay, so you'd probably say, oh, the reservoir is empty, all right? So it takes 50 hours there to empty that reservoir, right? All right, so again, those are very basic questions. Now, let's get to the tricky question here. We want to take that graph and we want to convert that to a formula, okay? So that's something that we do frequently in the class. Either take a formula and make a graph out of it, okay, or sometimes we go vice versa, right? We start with a graph and we want to see if we can start with a graph and see if we can write down the formula. And if you can write down a formula for this piecewise function, this really gives you a good understanding of piecewise functions, okay? So let's see if we can write down this formula. Look, the formula is going to have also in it, just like the graph, the formula is going to have 3 pieces, okay? So a formula for a piecewise function is a little bit more complicated than just the standard functions that we've seen up to now, all right? We're going to end up with a formula with 3 pieces. I'll show you how we can combine them, though, into a single entity. So I'm going to number the 3 pieces of this graph so we can write down the 3 pieces of the formula. So I'm just putting those numbers in there for reference, okay? There's the first piece. There's that straight line that's, increasing from left to right. And then there's the middle piece. And then here is the the third piece, right? This line that's going down from left to right. Let's start with the middle piece. That's really easy. I want to see if I can write down a formula for this graph, right? Okay, that little horizontal line right there. Okay, well, we already talked just a few minutes ago about what formulas for horizontal lines look like, right? So what's the formula for that simple piece right there going to look like? What do formulas for horizontal lines look like? Going to have y equals something. What's that formula going to be? Has zero slope. That's right. Okay, so it has zero slope. So if you want to fill that in, you can. It has zero slope. So you're going to be multiplying 0 times the x, right? Okay. But it can't just be 0 times x, because that's just y equals 0. But what's the other piece of the formula here? 8, right. Okay. So really the formula to get there is y equals to 8. Remember, for a horizontal line, the formula is going to be y equal to a constant, just a constant. In this case, the constant is 8, right? Because you can see that point, right, 30, 8 has to be on this little horizontal piece. Oh, so there is one piece of our piecewise function formula, y equals to 8. All right, so we got that one pretty fast. Let's see if we can get 1 and 3, okay? All right, so 1 is obviously a straight line, right? Okay, so what do I need to write down the formula for a straight line? So y'all have done this now about 500 times, okay? Oh, by the way, I forgot to mention, I was going to threaten you, right, with the test. So the test is coming up, okay, right, okay. And here's one thing that you, of course, will have to do, right, is write down formulas for straight lines. The sample test is posted, so I sent an email about that, but if you didn't get the email through Course Compass, it is posted. The sample test for test number 2 is there. On the Blackboard page, okay? So you can print that and start working on that. The test is not till next week, though. Next Wednesday, all right, is when the test is. So October 30th is the test, second test, okay? And, of course, it's going to be largely about straight lines because that's really what we've been doing ever since the first test, all right? So let's write down the formula again for this straight line, right? So to write down a formula for a straight line, right, what piece of information do you need there? The slope, right. Really just the slope, right, okay? And then a point off of the line, and that's really all that you need, okay? Well, what is the slope here? Well, let's calculate it. So the slope for piece number 1 is going to be, let's see, we've got 2 points here, right? So it's easy to use the slope formula. Let's see, I would get 8 minus 2. That's the difference in the y-coordinates, right, between these 2 points? And then over what, 20 minus 0, the difference in the x-coordinates for those 2 points? So I get 6 over 20, which you can, is that 6? Yeah, 6 over 20, which you can reduce a little bit to 3/10. So the slope for this piece is 3/10. And now you can either use this point to write down the formula for the line, but here we get a little bit of a break because we know the y-intercept, right? The y-intercept is 2, so that makes it easy to write down the formula for this line. It's just 3/10 x plus 2, okay? Because you can write the slope and the y-intercept there, right? So there's piece number 1 of our piecewise linear function formula. And then what's the third piece there? Well, we have to calculate this slope, right? So let's compute that one. So I get, let's see, the slope is going to be, I got these 2 points, right? So what's the difference in my y-coordinates there? That's 8 minus 0, right? And then divided by what? 50 minus 30. Did I do that right? No, I did it backwards. 0 minus 8. So I have there minus 8 over 20, which is What does that reduce to? Minus 2/5? Now, for this line, I don't know what the y-intercept is. If you extend this line, it's going to go way up here, so it's going to have a very big y-intercept. I don't know what that is, but I don't need to know exactly the y-intercept, right? Because I can use the point slope form. So I have y is equal to minus 2/5, and then you can use this point or this point. Let's use this first point. So I have minus 2/5 x minus 30, right? And then just add on the 8, okay? And there's your formula. Not quite simplified form, but that's good enough, right? There's the formula for that third piece. All right, now, how do we combine all of those pieces into a single formula? Well, it's going to look something like this, okay? Just write y equals 2, or you can put f of x equals 2, and then just list the three formulas, okay? So to sort of group those together to indicate this is a single function, I'm going to put a big brace here. We're not going to put a brace on the other side, though. Just a big brace here on the left-hand side. And then let's write down the formulas. Let's see, what was the first formula? If I can remember there, that was what? 3/10 what? X plus 2, right? That was the first formula. And then the middle formula was 8. And then the last formula was minus 2/5 x minus, was it 30? Yeah, plus 8. So you really just write down the the formulas for the three pieces, but you just kind of group them together to sort of make this into a single function. Now, there's one thing wrong with using this formula. If you just have the formula, if I asked you, okay, I see that formula, tell me what is f of 10, okay? So you've got the formula, right, okay? You should be able to evaluate f of 10, right? The y value that matches x value of 10. But that's not quite possible to do, right, looking at the formula, because you don't know where to plug the x in, right, okay? You don't know if it goes in this or in this or in this piece, right? From the graph there, Joshua, which piece should the 10 be put in? Yeah, it should go in the first one, right? Because here's 10 right here, and where x is 10, right? The first formula applies, correct? Okay. But if I'm not looking at the graph, I don't know that, right? If I just have the formula, I would know which function to put that in, okay? So we have to add a little bit more information into our formula. We have to get a little recipe here on when to use each piece, okay? All right, so let's look at that. When are we going to use the first piece? So for what x values will we use the first piece? Where does x start at? Well, where does the graph start at? 0 on the x-axis, up to where? 20, right, okay? So let's write that down. X has to be bigger than or equal to 0 and less than or equal to 20. What about for the middle piece? So for what x values do we use that middle formula? 20 to 30, that's right, okay? So just write that down where you're going to use, for what x values you're going to use that middle piece. And that's between 20 and 30. So notice we're writing down a compound inequality here to tell us when to use each piece. What about for the last piece? X is between what? What? 30 and Where do we have to stop at there? 50, right, okay. It can't go above 50 because the reservoir gets empty at 50, right? So in the piecewise function formula, you're going to write down the formulas for your pieces. And then you also have to indicate a guide here, right, of when to use each piece. So for what x value, you would use either this formula or the second formula or the third formula. So it comes out a little bit clumsy, not as pretty as the graph, right? Okay, but it's useful, all right? So that's the formula that corresponds to that graph. So if we were to evaluate f of 10, right, from the formula, we would say, oh, let's see, 10. 10 is between 20 and 0, right? So I know that I'm going to plug 10 into this formula. So we end up there with 5, okay? All right, let me give you one that's already created here. So here is not a graph, but there's a piecewise function formula. So see, notice it's got the two pieces, right? The two formula pieces. And there's our guide there to when we're going to use each of the two pieces. I threw in the extra word if there. Sometimes you'll see that in these piecewise formulas and sometimes not, okay? All right, so let's see if we can evaluate this function f. If we can't evaluate it, then we certainly can't do anything else with it, right? So what would f of, let's see if I can get all that on the screen. So what would f of minus 4 be? So how would you know to evaluate f of minus 4? Well, you got to figure out, is minus 4 in this set or is minus 4 in this set? So minus 4 satisfies which of these inequalities? Yeah, the first one, right? Because minus 4 is bigger than or equal to minus 4, but at the same time, less than 2. So that's easy, right? To evaluate f of minus 4, you just plug it into x minus 1. So we get minus 4 minus 1 is minus 5. What about f of 0? What's the y-intercept here? That's what we're calculating here, by the way, is the y-intercept. So what's the y-intercept for this piecewise function? 0, that's still in the first piece, right? Because 0 is bigger than or equal to minus 4, but less than 2. So use the first formula. So you get 0 minus 1 is negative 1. So when we make the graph of this piecewise function, it's going to cross the y-axis at minus 1. What about the last one there? F of 2. Yeah, notice 2 is going to be bigger than or equal to 2, right? So we use the second formula. So we get minus 2 times 2 there, or minus 4. So if you know how to read that formula right, it's pretty easy to evaluate these piecewise function. What's the domain of this function, by the way? So what x values can you actually plug into this formula? Well, where does the domain start at? Negative 4, right, okay. You can't use anything less than minus 4, correct? And it extends up to past 2, right? Because this piece stops at 2, but this piece begins at 2, finally up to what? 4? Yeah, so your entire domain would be numbers between minus 4 and 4. Sometimes this formula is used, right? Sometimes the second one is used. All right. The last thing we want to do here, so we'll do this next time, is we want to make a graph of this function as well. So we've already looked at taking the graph of a piecewise function and writing that down in a formula. That's got to be harder than what we're getting ready to do, which is to take this formula and turn it into a graph, right? Obviously, when we make the graph, well, we can sort of imagine what the graph is going to look like, right? It's going to have how many pieces to it? 2, right. And So it's got two pieces to it. Each of those pieces is going to end up being what? Well, what are these two formulas for? What kind of graphs do you get from each of these formulas? What sort of curve? Linear, right. This is linear, and this is also linear. So when we graph this piece, we're going to get a straight line. When we graph this piece, we'll also get a straight line. So this line, which way is it going, up or down? From left to right. Does it go like this or go like this? Up, right. Why do we know it's going up? Slope, right. What's the slope here? Positive what? 1, right. So that's going uphill from left to right. So when we make this piece, get a nice line going up. What about this piece? Going down. Its slope is -2, so it's going down from left to right. Oh, so we have an idea of what our graph is going to look like. Going to have two pieces, two straight lines, one going up, one going down. Okay? Now that gives us a pretty good picture already. Well, next time then we'll try to make that a little bit more accurate. All right? So exactly what does the graph of this piecewise function look like? And it's just going to be the matter of graphing two straight lines. Okay? That's all we have to do. All right. So we'll graph that one next time. Just to warm up, and then we have this sheet that I gave you that's all about piecewise functions. So we'll go through that activity, okay, after we finish graphing this one. All right, so remember the quiz. You've got a quiz that's due tonight, right? Okay, so that's on that prior homework.